Test, test. Test, test passed. How are you? Thank you, thank you. Hello, Max, how are you? Thank you, thank you.
No longer I can just say. No, no more, no progress.
Oh, how are you? Over there. Let's maybe wait another minute or two. Well, we already have a quorum. Like 5 out of 9 is a majority, in case we need to vote. I know that David will come later because he's presenting at a conference until 3. Aha! A privileged group thinks that they have a right to come later. I need a volunteer to substitute David by the machine. So in the simplest way, just you push buttons.
Yeah.
It's too complicated. Just one and two. They're preset for 1 and 2. So it's minimalistic. Many thanks, Vanda. Today there is a chance to finish earlier because amount of materials to derive is very small. It's deceptively suspicious. So we need basically maybe like 2 or 3 equations, but one is like missing meaning and content very easily. I was missing it like 20 times before I got what is going on. So it was presented to me in my like undergraduate and graduate classes, and I like equations are too simple, they do not deserve my attention. The major effort will be matrix multiplication that 2 4 by 4 matrices will be multiplied, and I want to share joy of this exercise with everyone. So you'll come and take like 1 row and column per person, and then maybe do it twice. But the rest is just mumbling, and from my side, I'm trying to get to right point. Before we go to the material, I wonder, did you enjoy the style of presentations as midterms? It's better than written exam, I hope. So what do you think if you do a final in the similar style? Okay, I was debating if one can just summarize, like chop the materials from the class and then do the, but maybe some of you would like it, but it would be boring for me to hear the same material again, right? So what about if we do again, considering class attendees as a team who saves the ship from sinking and patching the holes in the ship, and just covering those materials that are physically impossible to include. So I will share. So the one with black star, where you write down your final decisions at the end of the class, and here are just pieces of paper with the list for you to get acquainted and decide what you may want to prefer. If there are, I wouldn't say conflicts, but if there are several subjects that attract more attention and other subjects that no one, I'll take responsibility of mitigating the conflict and making sure everyone is happy. And we need to give maybe not full preference, but some sort of preference to David, because he's not here at the time when we vote, or you prepare and we vote when he shows up, something like this. If maybe during the break or after the break, if you look through and have questions, I'll explain what they are, but one can speak endlessly about the stuff. Literal versus averaged Bloch equation, types of features of the bath, microscopic goal to find T1, T2. Features of noise. I'm not able to read my own handwriting. Probably no one else as well. Double-side Feynman diagrams, 2-step evolution, matrix multiplication, and analysis. Thank you for the attention. I thought I writing it only for myself and no one cares. So we did successfully completed 2 chapters, and overall goal of our meetings here is to be able to describe quantum dissipation, to fight the big lie of basic quantum theory, where systems are considered isolated and in real life they're not isolated. In the first after the break chapter or third chapter overall from the new year, we worked on perturbation theory and Fermi's golden rule. In the second chapter, we did an average over ensemble that allows to get photon echo and more simple things. But in everything we were doing until now, there was an important simplification. The dynamics, and this part of the course is focused on the dynamics. The dynamics did have a character that one can characterize as energy conserving or unitary or elastic or Hamiltonian. And you have seen the manifestation of this feature in the effect of photon echo. Major, I do not know how to formulate it. It's typically one gets intuitive vision of what these words mean, but it means if we have an observable going from time t1 to time t2 by some mathematical procedure, I don't know. If we set up a mathematical procedure inverted, if you just go backwards in time, you set up the time is increment is negative time, then one can go backwards in time from t. That's right, maybe in one instead of one of two, like past, future. And if we invert the mathematical operation, we can go back from future to the past, observable in past time. Reversible. It's reversible time evolution. We do get a lot of interesting effects and a lot of connections to real life with these features, but not if you are big supporters of statistical thermodynamics, you have heard stories and jokes about things being irreversible, right? Like Boltzmann was trying to find an argument to his opponents and blowing dust into their faces, asking if you can reverse it, please do. So some processes are irreversible, and it is time to slowly start store them and complete by the end of the course. So it was correct up to now, but from now on, or maybe from Thursday, it will be wrong. So we will focus on the irreversible dynamics. In the lab, in the last lab, we were assuming that there are a lot of replicas of our system of interest, and I admit that our system of interest is very oversimplified, for example, of only 2 electronic levels, but one can go too far with if one wants to be short in time. But we had ensemble of replicas which are slightly different from each other, but their differences were static. So we still, each of them can be reversed backwards in time. In the absence of external radiation, each of these two-level systems was maintaining its energy. So if we created with pi/2 pulse, it was in the halfway between ground and excited, and it was staying halfway between ground and excited. We did have accumulation of phase in XY plane, but we didn't have any change of the population. And this is, in some sense, main goal of the course, to get an idea, get a mechanism for population relaxation, to see a mechanism how system comes from not only from pure state to statistical mixture, which can be approximately done by average over ensemble just with different phases, but to model dissipation of energy. So if system is prepared hot and placed on the cold stove or cold support, it will get colder. If it's prepared cold and put on a hot stove, it will be heated up. The mechanics of this process is absolutely absent in pure quantum mechanics. So when needs a little bit of statistical thermodynamics of some basic ideas from there. So it is maybe counterproductive and too abstract to give general idea. Maybe we can look at some practical examples. So what may happen to two-level system, which mechanisms would lead to its losing its energy? We need a mechanism that will affect not only the phase. Before we had a Bloch sphere, and in the movie that you have either submitted or plan to submit, we started at the pole, and then go across, and then it was relaxing backwards to the center, right? So coming into statistical mixture. But in the absence of excitation, it was moving only in the XY plane. And we do want a motion along a Z plane. So intuitively, it should be something that does affect, does depend, it is something that is connected to the way how it is excited. So we did consider two ways of working with ensemble of two-level systems. One is that we did solve for either density matrix or as I'm poor in indices, in either density matrix or projections over time. Consider that we have several replicas, and we performed literal average over ensemble. And then we were using this to predict some properties. Another opposite way is to make an average equation of motion for this quantity right away. So to find what would be the DDT for average density matrix or DDT for average projection of spin. Let's try to remember the Bloch equation because we want a little bit more specifics. So if you do have a pseudo spin, let's use sigma. Sigma 1, sigma z. So we do have coupling between y and x for precession, and we do have coupling between z and y for excitations and de-excitations. So now I need help either of the class or on my cheat sheet for science. So there are no imaginary units, right? So spin projections are all real, correct? And they never get complex.
There was a complex unit in SY somewhere, wasn't there? Okay.
If we do transition from density matrix elements to SY, we will have an imaginary unit for conversion because both diagonal elements are imaginary, and if you want to bring them into real projections which relate to magnetization, right? They all should be real. So the question that I want to extract from either cheat sheet or from helpers, do we have all pluses or somewhere minuses in front, and do we have factors 1/2 anywhere? Everyone agrees? I don't mind. We can admit any notation. Just let's make it consistent with what we did before.
That sounds right.
So delta over 2 and omega Rabi without over 2. Okay. As soon as just delta. Okay.
And then you
So-
can have an over H bar.
Huh?
You can have an over H bar.
So delta is energy, and we do need a frequency. Okay, agree. And here is the frequency. We do not need H bar. Do you have pluses everywhere, or they alternate?
One of them's gotta be negative.
Hmm?
One of them's gotta be negative, I think.
So which of them?
Let's see.
So here.
Other one, I think.
I should be delta minus.
Negative in front of delta x also yes has negative back. Yes.
Okay. And then here it should be plus.
Yes,
Different signs. Okay.
and here is negative.
Here is negative. Here is positive. Okay. Feel free to correct. It's long to derive and hard to memorize, so it's better to use some records. Tori, are you okay with following without over 2? Okay, thank you. Okay. So if we follow the the same color. If we add summation over ensemble, I believe then the factors should also take into account averaging. And in addition, there are two terms which serve as a price for having simpler equations, for avoiding resolving this equation again and again. So the two terms that correspond to precession get neg minus 1 over T2 and then itself minus 1 over T2 itself. And this is transversal. And the population inversion gets 1 over T1 is the average longitudinal. So if we never, if our ambitions do not go beyond two-level system, then the goal of the course of the rest of the course in a narrow sense can be formulated as how to find T1 and T2. And for T2, I believe we already derived at the end of previous meeting that it should be something like 1 over with maybe with some factors for the distribution of frequencies for the offsets in the ensemble, right? Does it click anything? In case these two-level systems are distributed ground state, excited state for the first system, excited state for the E1, E2, E3, E4. And here we have ground 1, ground 2, ground 3, ground 4, right? Do you remember this figure? So they have different delta, either positive and negative, and the width of the distribution of all offsets is delta naught. So the width of this distribution already gives us the transversal relaxation or transversal relaxation time. So we already got it. So we can narrow down the task, simplified task for the rest of the course as a find a microscopic way to obtain T1 longitudinal relaxation time. Let's click on the class camera, not instructor, but class camera. And let's just discuss any opinions. Feel free to say anything. It is. I realize that it is set up and you are not preparing to answer anything. But which mechanism can be responsible for continuously losing population, no matter if you go forward or backward in time? Mm-hmm. Okay, vibrational relaxation. Okay, yeah, thank you, Adam. Steven, anything that comes to your mind?
That goes forward and back.
Yes, we should get relaxation, whether we go forwards or backwards in time, it should relax anyway. And my goal is to present it how we can do it mathematically, but what would be the physical picture? Like, okay, emitting phonons. So you agree with Adam? Max, anything, how do you see mechanism?
Not really sure. So it's symmetrical. Oscillations are symmetrical.
So something should be dealing with symmetry. Maybe something should break the symmetry. I understand the challenge, but to make sure that phonons are emitted both way, no matter we go forward or backwards in time. Any ideas? Okay, so what I learned from you guys that you want to add another degree of freedom that interacts continuously with our system of interest. Right? Vibrational or rotational. Patricia, anything? Let's be confused together.
Just kind of confused, what is, the time has to do with relaxation? Like, if it goes forward or backward. To do with relaxation. Like, I was just confused, like, it's supposed to.
So here is a philosophical aspect. If we have a procedure that describes emission of energy, relaxation, right, then the energy of our system of interest will decrease. By now, we do not have any results, but may decrease exponentially. If we do not maintain this relaxation, no matter forwards or backwards in time, if we invert time, which is hypothetically okay, then system will gain energy exponentially and will just everything will explode. So we should prevent it. Okay. Okay, but thank you. It's an important discussion.
It's like we need some kind of thermal bath to exchange entropy with our system versus
Yes,
something of that.
and we will arrive to. So we will start it on Thursday. There are even simpler ways. But what is specific about thermal bath?
It allows us to exchange energy between our system and the outside world.
With
So then statistical thermodynamics kicks in.
okay, so in James Cummings models, if you drive our two-level system by optical or electromagnetic excitation, there is also exchange of energy. So what is missing there? And then you told the word statistical. What is missing? How do we make a bridge between these two worlds? Huh?
I was thinking that was that what we discussed the last, to make sense to bridge between statistical, what I will introduce density metric.
Yes, density on mathematical language, it is necessary but not sufficient. We need one more idea.
So James Cummings, we only have the electronic degree of freedom between our two levels of our atom and the photonic degree of freedom from the light in the cavity. So do we just need the photonic degree of freedom?
Or, well, simplest way is to have like many other photonic degrees of freedom representing a bath and making sure that each of them is in this thermal state. If you want
So
to,
like several different wavelengths of photons?
right.
Okay.
Right. Arasa, any?
Go to further connect the idea of entropy, like that's a irreversible process.
Okay.
I mean, measuring it.
Mhm.
I-
So you are promoting thermal equilibrium should be somewhere.
or once you get to thermal equilibrium, it's not like you can't reverse the process to see where you were initially with the entropy.
Okay. Okay. Yeah. Thank you. Well, any comments? Okay. Yeah, sorry, Adam took it first. Next time we should start journey from other side. Let's go to instructor and then number 3. Yeah. And one can record so that it will be same thing again and again. So after you arrive to write arrangement, one quickly go to between like number 3 and preset save 3 immediately. And maybe a couple of times between them, preset save 3 and then should hopefully it should work. What if our 2-level systems are not static, but they are coupled to nuclear degree of freedom, and they are just represent this transition energy at a selected value of reaction coordinate. As soon as we go into different value of reaction coordinate, they will experience different transition energy. And if the nuclear degree of freedom performs random motions, then the transitions will be not as reversible as they were before. Another thing that I can imagine, I can try to imagine, I don't believe it completely, but I need to say something. In all textbooks, one skips this discussion completely and just goes into equations that Lola did an absolutely perfect presentation past this point. But this point was, I remember also she was asking questions because all textbooks arrive and tell, like, let's consider autocorrelation function and do everything starting from there. And they do not explain why and what it relates to. So I will perform very poorly and do some pathetic diagrams and explanations, but maybe they will help us to overcome this point and have maybe not fully correct, but at least continuous picture of what is going on. So suppose I have my favorite 2-level system, which is in the excited state. Then we do have an ensemble of, maybe it is a monoatomic gas molecules that collide to each other. So there are other replicas which have the same nature, excited. And let's assume that only one is excited, all others are in ground state. So they experience random trajectories and they collide from time to time. So they come to vicinity, and when they come closer to each other, there are mechanisms for exchanging energy. One of the mechanisms of exchanging energy was presented by Patricia at the very first presentation, at the very first part of the class through Forster, right? So if the 2 electronic systems are close to each other, by dipole mechanism, they can exchange energy. So if it moves slowly, velocity approaches 0, it comes, they linear, they stay close for long enough time, they may exchange. This one will go to the ground, this one goes to excited, or they exchange their excitation halfway. And then we still monitor our primary, when this depart, we look further on the system. Then maybe next system comes, and this is by tangential line with high velocity, well, not infinity, but big enough. It interacts with much shorter time, so it gets a little bit of exchange of energy. So transition of the state. When they are in contact, it is one of your favorite problems from the part one of the course, when two level systems interact and they have some common quantum state, but as soon as they depart, they become independent two level systems again. And then another one can just do not interact at all. So this is something most practical I can think about. If I want to make it a little bit more rigorous, a little bit more easy to describe mathematically, I may consider my world bound only to this primary two-level system of interest, and the others can be considered as a source of Rabi frequency, which is very much time dependent. So when no one is in the vicinity, this Rabi system, Rabi frequency is 0. When they are coming to in a close vicinity, it comes to its maximal value. If it is tangential, it goes to like smaller than some pre-made constant. So I know it is very poor argument and illustration, but it is the best I can do. If you find better explanation, I would be in any book or online, I would be very curious to learn. So it is like a lifelong task. Now, do you have any objections or more or less agreeing with this poor argumentation?
Why would the frequency be 0 in the isolated case?
It's not frequency, it's Rabi frequency.
Right.
So if we assume that if you consider the external system is exchanging energy by virtue of photons.
Okay.
It means temporarily it has electromagnetic field that induces transitions, right? Because how else we can explain mechanics of the interaction between two level systems? We should admit that one releases photon, another emits photon.
Okay.
And photon means electromagnetic radiation. Yeah. So our primary system of interest experiences external electromagnetic radiation of different intensity and different phase.
Okay.
So this omega Rabi of time is internal dipole of our primary systems times this external electromagnetic field, which depends on the environment. So it depends on which neighbors are coming closer or running away from the system. So all environment does create an average electromagnetic field affecting our local system, and this field will be quite random because all molecules or atoms in ensemble move quite randomly. When they would be static at a certain distance, one can find regularity, but when they are moving, it will be something very irregular. Irregularity, the random nature of these collisions will be reflected in the way how the transitions how the transition in the system will experience this hypothetical virtual electromagnetic field.
So are we assuming that we're not driving the electric field anymore? We're just kind of letting the system exchange its own photons without pumping any more into it?
We do not consider any formal electromagnetic radiation.
Yeah,
We have one excited and others empty. But when they come closer, we can describe their interaction in terms of electromagnetic radiation.
Okay.
Okay. It's not perfect. I see even more loose sides of this analogy. Okay. But if you see any loose sides, I'm very for it. Now, so I am going to, so this depends on T, and it comes from environment, so it will be very random. So I do need to, please do not move, I will continue in this little spot. So I do want to add a little bit more specifics, a little bit more rigor to the word random, like what do we imagine under the concept that it is a random electromagnetic field? It's oscillating quickly as an electromagnetic field, but we already admitted interaction picture, rotating frame, so that everything can be computed easily. So it's more like an intensity. So electric, well, Rabi frequency. Rabi frequency can be with time. Can be big and positive during the time interval we have a good interaction when we have a collision. It will be, say, 0 when our primary system is free and not interacting. It can be either positive or negative when time interval when it interacts with maybe in shorter, quickly passing on a far distance. So not collision, but how to say, tangential touch. And in more, if you want to continue this time axis, we can just randomly assume different height of this Rabi, different height, different sign, right? And different intensity of the Rabi frequency. So this is something random. If we want to, please do not move, I still continue here. And it's almost dry out, but I will try to draw with different color.
I have other.
Oh, yeah. Well, thank you so much. You are saving several groups and classes continuously. So if I want to put here second axis and call it actual electric field without all this rotating frames, it will oscillate quickly. And here it will oscillate. But here I started from, like, cosine started from 1. There is no guarantee with that phase at a time when it starts interacting with the same. It may start with like negative sign. Right? So it will start with different phase. So it is not continuous when we go to different period. So it's different amplitude and different phase. Quarter phase. Different amplitude and different phase. So the goal is to explore what would happen to just one single two-level system if it is affected by noisy driving field. Okay, so let's just explore the consequences. I'll just return it and borrow again if I need, because I have a fear to like hide or lose
I know where to find you.
and escape to different states. Okay, so any questions about this goal? So it is a little less loose than this colliding atoms, but it is still very much skipped in textbooks, or it is spoken when it's skipped when one is speaking about relaxation in terms of density metrics, and it is slightly discussed when one is looking onto subject 12, Langevin equation and Fokker-Planck equation. So people start speaking about noisy environment and how it drives relaxation. Also in Brownian motion, there are some discussions of this noise. Okay. So I'll probably keep telling stories in this loosely organized motivations and models until the break. And after the break, our main goal would be to collectively multiply two 4x4 matrices. Just get ready for it. Okay. Yes, I know what I want to draw. So let's go to other side. With your permission, I'm going to erase this panel and do something. We can scientifically process and analyze noise, even if it is not our major specialty. Although there are some noisy scientists, like it is really important in electrical engineering, designing radars and signal to noise ratio. But if you do have this noisy function, we may characterize it. We may design procedures that would characterize them. We do want to insert this noisy function as a parameter in our Bloch equation or equation of motion for density metrics. But before doing this, let's discuss how to characterize degree of noise, or what can we say for sure. So some simple standard protocols, like they may not reproduce the whole function, but at least some features, same as we do in synthetic lab. Well, I don't have authorization to enter, but after something is synthesized, one uses different characterization techniques to give like fragmentary features that after all characterization one can recognize what it is. So one can integrate from initial to final time and find average of this noisy function. I don't know what to use, angular brackets or bar. One shouldn't use either one or another. It's a little silly to do both. I do not have arguments for my next statement, but in fact, if we accept dt, if you accept that it has a random phase and random amplitude, it is quite standard that expectation value average of this Rabi frequency will go to 0. So, and if we stop our consideration at this point, if we rewrite our Bloch equations that maybe I should have kept here, because otherwise I will need to recall it again. If we stop at this level of characterization of noise, there will be no transitions at all. So if instead of external driving field, we have only these collisions, average Rabi frequency will be 0. And if you stop at this point, it will mean that there are no relaxations. There's just no change in the population at all. But the whole goal of this activity was to get change of population. And we had a hope by looking on this smiling symbols colliding to each other that it may give us some relaxation. So what do we do if the first order treatment proofs is found to be 0? Yep. So what if we do this noisy minus its expectation value squared, and then do another average. I just misaligned thing. I'm going to cut and paste it a little to the left. And then, yeah, I can write it down that this noisy field minus expectation value squared dt. And if we admit that the expectation value of the first order moment was 0, then we will have only noisy field squared, right? It is an exercise that probably all of us are doing when learning how to process experimental measurements, like standard deviation. It's like omega squared minus 2 omega average plus squared. And if we add another averaging, then so this is already 0. This becomes 0 because another averaging, and then we keep only the quadratic term. So noisy Rabi frequency integrated squared, integrated over time. Again, I do not have well-developed logic and story, but there is a feeling that even if the process is very random, even if you assume this random collisions, in case when we expect that moving to the second order, including the average of the standard deviation of this noisy function from its mean value, may do something good to our time evolution of two-level system and is expected to contribute to the relaxation. Yeah, before going to the break, I'm going to go to another board and draw something theoretical that maybe I will need to erase for the final version of the recordings. I should have this one. How to on one hand, we found that expectation value of the second order of the square of this noisy function is non-zero and may serve us. But on the other hand, in our Bloch equation and equation of motion for density metrics, we have Rabi frequency only in the first power. How can we introduce second order? How we can connect these two things? London may prompt like, oh yeah, you use second order perturbation theory. but how can we wrap our mind around it? Why it is needed? And I have something that I'm not confident, but it's a candidate to be erased. So if we take double-side Feynman diagrams introduced by Tori, right? And suppose we do have system in excited state. We describe it by density metrics, and we want to describe the emission or recombination to the ground. So we need to arrive to the density metrics that describes the ground state. But by the way how the things are working, a single order perturbation, which we can think about as a pi/2 pulse, affect only left or right side of this double-side Feynman diagram and do not change the whole density metric. They change only one of the branches. So if I introduce an emission of photon, and just thinking about pi/2 pulse, it will change after this time t1. It will change system to ground here in forward going, and still excited in the backwards going branch of the density metrics. If I want to arrive to the ground, I need to have a second perturbation to emit at the other side of the world to conjugate it. Then after this time t2, system will arrive into the ground. It's again a very poor argument, but it connects things and tells on one hand we have a second order momentum as a momentum not in a mean of the velocity, but moment in the mathematical statistical sense. Second order moment that is non-zero and may help us. On another, through this argumentation, we kind of get an idea that one needs a second order perturbation to get a transition from excited to the ground. And who comes first and which side comes first is resolved by making integration, like rho at final time can be rho at 0 time, evolution minus I h bar interaction Hamiltonian dt plus I over h bar interaction Hamiltonian dt, where this one is can be expanded in a single perturbation this one into another, and after going from here to only first term, it will 2 pages left. It will be integrals from 0 to t dt1, and then from t1 to t2 to t2 d tau, and then it will go. It will provide rho of t. Here will be this interaction Hamiltonian at t1, t2. Here will be the density matrix, right? And I probably need to cut it from the recording because exact minus I h bar, and one needs to watch for constants. But propagating from past to the future can be done in the second order of the interaction, and then it will include 2 interactions, and we may connect it to the fact that mathematically second order moment is non-zero. Why one is not one is not staying at the first order only? Because if we stay with first order only, we know mathematically it will give 0 upon average. So it is a we are induced to do so because of the features of the random noise. So if the outside noise is random, we are mandated to skip first order because it is 0 and go to the second order. It is, yeah. Let's do a little break for like 4 minutes, 4 or 5 minutes, and then we'll go to multiplication of matrices.
Friday, what is your thought about being trained in these places?
Oh, welcome back. Were there many visitors? Okay.
I did get some sleep last night, it just wasn't enough to catch up. The lack of sleep has been bad for, I don't know how long.
Then these are- once you don't take it. I didn't see you right at 7.
Oh, you're back here, right? So, yeah, this is a little better than the one I was showing before. Oh, just to have the equal opportunities, here are we are doing a little voting on the subjects, and I'll pass the black star. So write down your choices and pass it around so that everyone completes. Yeah, I didn't notice that it happens with people. Okay, so we do have a very powerful, very strong tool that saves a lot of effort and allows us not to drain our brain too much. So as a result of our previous chapter, we do have an explicit Liouville operator, super operator that propagates two-level system density metrics from the past to the future. If in case we want to find propagation solution for the density matrix evolution on a short time interval. Instead of solving differential equation, rho dot equals L rho. Instead of solving this equation, especially if the Liouville operator is expected to be time dependent, one can look at the short time intervals and find the solution, the propagation on a short time in terms of time dependent perturbation theory, or basically one can take the solution of t as e L of tt rho 0 and just expand this exponential into Taylor series, right? If we know that this thing changes over time, we can do it in a careful way so that our expansion will include the Liouville operator at different times. So here I'm attempting to write it down. So we start with unperturbed past. Then we apply the Liouville operator, which includes interaction with this noisy field at certain time, and it gives correction of first order correction at the next time. If we do want to apply interaction with noisy field for the second time, right? We do want just to apply this interaction once again to the one that was already declared, right? And then we will have the Liouville super operator, a different instance of time applied to our unperturbed density matrix 2 times, and then we can make it correct by putting like integration, right limits, and see what is going on. If you see errors, please correct or let me know. I need to improve from year to year. If we, so by now no one objected up to here, right? And up to this point, we were assuming that our Liouville operator originating from the random Rabi frequency. So it is Liouville, which is also random and time dependent. Here, I'm going to express the last non-trivial, last more or less new idea for the class in this meeting. The rest will be just mathematical entertainments of multiplying matrices. So what if we agree on this expression, the second order correction, t plus 2 delta t, as applying Liouville operator twice at different times, t plus 2 delta t and t plus delta t. So we do have this expression, and we do not. Well, if anyone objects, you're very welcome. I would admit any constructive criticism or indications of errors. Thank you. So what if we borrow our way to characterize mathematical functions in that we did on the other board to this expression? What if you want this equation to be a little bit more universal? what if you want it to be applicable, not at a specific time t and t plus delta t, but universal? What if we perform, if you find average density matrix, which will be like summation of density matrix at of all possible realizations of this random noise field. So we wanted this equation to be applicable at any point of time. So in some sense, we average over any point on the trajectory. So we put here average over all possible points of time. In the same way, we do want to perform an average for this product of two Liouville operators. If you would do individual average for one Liouville operator, there is a chance that we will get something zero. But if we would perform an average to the product of two Liouville operators, it should be related to expectation value of omega squared, and it should be non-zero. If we would want to do it very meticulous, very rigorously, and I promise we will do it before the end of the class. Right now, I just want to skip all details, both for simple life of you and myself, and just get basic ideas. So if one wants to do it very carefully, instead of just square, it should be a time correlation function, t plus tau, t without tau, to allow a little bit time delay between instances of interaction. But as of now, for just very quick assessment of the main idea, we can just make this connection. Okay, and it is not equal; they're just related. So once again, let me reiterate where we are, and then we will get ready to practice matrix multiplication. The goal of the rest of the class, of the rest of the meetings, is to find a microscopic way to predict the longitudinal relaxation time, T1. We noticed that in simple average over ensemble that we did in previous meetings, there were no longitudinal relaxation. Energy was conserved and all dynamics was reversible. We hope that we get an noisy bath, which can be imagined as a collisions with random replicas. We hope to get the longitudinal relaxation. For the noisy bus, the first order moment, expectation value of this Rabi frequency of the noisy bus is often zero. It gives a justification to jump to a second order. And we do make a connection between second order perturbation theory on one hand and the fact that second order moment of the noisy bus is non-zero. When we merge them together, we arrive that time evolution for the small time step of the density matrix is expected to depend on a product of two Liouville operators. Okay? No one objects? Okay, so if we believe in this statement, then the only thing left to do until departure from this meeting is to remember how the Liouville operator looks for two-level system, write it twice, and practice multiplication. And then you will be surprised and you will see something really interesting and useful upon seeing the result. So I'm going to the other side, and I'm going to set up the sandbox, and then I hope that everyone will come to the board, except Hadassah, who was wise to leave before that, and do a couple of rows and columns. So we did this little versus average block equation types of. I didn't do it, but basically we do noisy bus, and later on we will do literal quantum bus with taking into account, instead of noisy environment of unknown nature, we will microscopically describe Hamiltonian of the stuff that interacts with our primary system. So goal is to find 1/T2. Features of noise, they are here. Double side Feynman diagrams we did just before the break. Two-step evolution done. And now we need to multiply two 4x4 matrices. Probably start with colors, and then we can write with black over it. So what I remember that there should be delta delta, omega 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 omega, omega 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 omega, 0 0 0 0 0. And what I do not remember is what are the signs. I orange bar, I orange bar. One of them is plus, another is minus. I think here delta shouldn't have divided over 2. Then the Rabi frequency will have imaginary unit everywhere. And in what we were deriving together in the class, I believe the pattern of signs was as follows: minus, minus, plus, plus, minus, minus, plus, plus. In the notes that I did a few years ago, the pattern of signs, maybe by an error, is different. So probably we'll follow what we did in the class, but if there will be some very suspicious answer, we can return back to what I have in the notes. To find the truth in the short time is impossible. So the pattern there was alternating minus, plus, minus, plus, minus, plus, minus, plus. But based on what we derived together this year, I believe this one is correct. And now I'm going to rewrite it once again, because we need to have the Liouville operator squared. If I do it with different color, then we can have red row and blue column. Bless you, bless you, bless you. So plus I h bar delta minus I h bar delta 0 0 0 0 0 0 minus I omega minus I omega plus I omega plus I omega minus I omega minus I omega plus I omega. So multiplying two square matrices 4 by 4 should be another square matrix 4 by 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if each of us does 2, then we will be done. So probably do 2, then everyone does 2, and whoever will go last will do just 1. Okay. So row by column. 0 plus I squared omega squared minus times minus is 1 plus I squared omega squared plus 0. So it looks like it will be minus 2 omega squared. And everyone is very welcome to correct. I am probably has the biggest affinity to make errors in the audience. So continuing the same row by the first row by second column. So 0 by I omega 0, I omega by I delta. So I squared omega delta H bar. Done here, done there. Then 0 times omega, 0 times minus I omega. Will be minus omega delta H bar. Let's do the thing first and analyze second. But I anticipate if we admit that expectation of the first order along the noisy trajectory is 0, this term will drop later. Okay. London. Oh, he didn't took your hands. I just wanted to wash my hands and tell that I'm not responsible anymore for them. In case. And you can do it on your own in the notebooks and prepare for your time to go into the stage so that you go quicker. So red row by first row by third column. First one is 0, second is also 0, and this one will be so negative 1. Okay, 2 minus times minus is plus, and I squared.
Would be high.
But if this one is minus and this one is minus. Okay, let's do the first row and fourth column. Yes. Omega squared. And then minus plus omega squared. It's again minus I. But negative positive, negative, positive. Okay. And please watch what is going on and feel free to correct errors. It is chance for an error increases exponentially with amount of elements in the circuit. So second row by first column 0, then I squared. Okay. Row by column. And everything else is 0, right? Okay. So then second row and second column. Minus omega squared. Okay. Minus delta squared over h bar squared. And the rest are zeros. No? Okay. Non-zero. So minus omega squared. Yeah, thank you, Max. Sorry? You'd like to? Patricia, you're the next. Just factor 2. Okay. Yep. Thank you. So second row on the second row, third column. Okay.
Negative I times negative I, -1.
Minus delta squared over h bar squared. Okay. And the next one, second row and fourth column. Yeah, thank you, Tori. Patricia. So third row, first column. Zero. First element 0, second element 0. Okay, and then third row and second column. Plus omega squared. Next 0. Next 0. The last one. Okay, yeah, thank you, Patricia. I think London is next. third,
So that'll
third row, third column. Negative delta squared, a bar squared. Okay. Row by column. Negative. Okay. Third row, fourth column, 0, 0. Minus time minus plus. Omega delta over h bar. And then 0. Okay, yeah, thank you. Oh, no. Steven, or well, if you want, you can go ahead. Or fourth row, first column, 0. Okay. 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 So positive of both, right? Okay. Yeah, done. And then the next one. And minus I squared will be just plus, right? Okay. Zero. Okay, excellent. Oh, Steven, go ahead. Steven and David do just one. So row fourth. If you need to go ahead. It's all recorded. I may hide it from general public, but I will share it with the class attendees. Or 0. Okay, yeah, thank you, Steven. David, join us for a little exercise. Okay, thank you so much. Landon, please do not move image. I will use the stuff here as a little cheat sheet to pass it on the second board. Yeah. If you find, go ahead. But I'm going just to transfer. If you would do it on the Zoom board, I would do just paste. Since time average of the for the random of the omega first power goes to 0, each terms of delta times omega h bar will be 0. So even if there are any errors in front of such terms, we don't care. But thank you for finding L plus 1. So let's carefully pass on the expression. So everywhere where we have product first order omega, you can do 0. So 0, 0, 0, 0, 0, 0, 0. So on the places where we originally had the Rabi frequency, now we have zeros, right? For the diagonal in here, you have minus 2 omega squared minus delta squared over h bar. H bar. Here on the other of diagonal, we have the same minus 2 omega squared minus delta squared over h bar.
That's all like symmetric.
H bar squared. Yeah, thank you. T plus 1. We do have plus 2 omega squared plus 2 omega squared in this place, and I suspect that here we do have an error. I would double check twice. I'm very unhappy with these two positive terms. So if you see what is wrong in this place, I would appreciate. And then we do have the plus 2 omega squared here, and then minus 2 omega squared there. Here we do have I squared, which means it is minus 2 omega squared, minus 2 omega squared here, and plus 2 omega squared there. So I hope that we didn't make errors and you agree on the top and bottom left and right corners. And it agrees with what I expect. Diagonals are okay. This blue marked things, it would be, I don't know, my homework, your homework, whoever finds and where is the error. I'm very suspicious with these two positive things.
Average down. So it should both be positive. But you just get plus minus I every time.
Okay. I'll double check. Those two are suspicious, but okay. Now let's refocus on the board number 3. So let's analyze what we have by now. So row 1, 1, row 1, 2, row 2, 1, row 2, 2 of time t. And here, if you multiply it by delta t squared, you'll get an increment for delta row 1, 1, delta row 1, 2, delta row 2, 1, delta row 2, 2. Any objections at this point? Or you accepting it as is? Accepting as is like a 7 used car. Okay, and I'm going to write it once again. There are several observations, and they are really great. We together did a discovery, and we share credits like 1/8 of the credit to everyone because we derived together. So when we had original equation of motion for density matrix with Liouvillean operator, all elements were complex, right? And we did have originally the following. I would do things in a simplified way. So to get change of the population, we were getting omega rho to 1, something like this, right? To get increment of coherency, we were getting some phase accumulation, rho to 1 plus I omega rho to 2, right? So to let me write it down in words. To increase population, we mathematically extract degree of coherency. So increase population depends on degree of coherency. Degree of coherency. The degree of coherency increment or degree of coherency was depending on population. So, which means degree of coherency and population were coupled. They were changing simultaneously in a way they depend on each other. So originally we had coherency and population were coupled, right? Now, I will redraw, summarize what we'll get. So delta rho 1 is, well, depending by delta t squared equals -2 omega squared rho 1 plus 2 omega squared rho 2. So in the equation of motion for or our stepwise protocol for increment of population is coupled to population. Population is coupled to population. Then next equation, delta rho 1,2 divided by delta t squared -2 omega squared rho 1,2 delta squared per squared brackets plus, I do not like this plus, but it's too it needs a sober analysis. So what do we see? Increment of degree of coherency is coupled to degree of coherency. Degree of coherency is coupled to degree of coherency. And I'm going to continue the rest of equations, but after I will complete them, we would be able to make a very important conclusion. So if we take into account only change of density matrix by a noisy but the coherency, degree of coherency and population are decoupled. So to those of us who professionally live by solving equations of motions for density metrics, you may have asked yourself or your collaborators, like, how dare we to solve equations of motions only for populations and skip coherent part? Because in the definition of density metrics, coherency is really important. Yes, it is important if you look onto reversible unitary Hamiltonian dynamics on a short time. But if we monitor only average dynamics in the interaction with noisy bath, coherency and populations are decoupled, and we can temporarily forget about all evolution for coherency and propagate only the populations. This is an approximation. If you really look on dynamics on a short time, one needs to bring back first order things that depend on non-noisy, on the constant parameters. But if you look on a long time evolution, it is a very good approximation that saves a lot of numerical efforts. So let me continue. So delta rho to 1 delta t squared plus 2 omega squared rho 1 2 minus 2 omega squared minus delta squared over h bar squared times rho to 1. So again, we see that degree of coherency is coupled to degree of coherency, which is cool, interesting, but our populations are not touched. They are getting decoupled. And the last one, delta rho 2 2 delta t squared plus 2 omega squared rho 1 1 minus 2 omega squared rho 2 2. It is really beautiful and nice. If we focus only on the equations for populations, and if we do a trick that take it not as a square, but like derivative over time, it's increment in one time steps, like replace this construction over time derivative. I don't know how to do it rigorously and which theorems to quote, but it's just increment. If you go time by time, you can replace this construction by ddt. So I'm going to erase the bigger equation, which is nice, correct, but we are going to focus on only two little things. Dt rho 1 1 equals minus 2 omega squared rho 1 1 upon average square of any real number is positive. So this one is positive. Overall constant is negative. Right? Real and negative.
Oh, wait, never mind. Okay.
Omega is electric field times dipole. We will admit it is our electric field is real.
I thought it was supposed to be rho 2 2 for a minute there, but then yeah, it's not.
Plus 2 average of omega squared rho 2 2. Then this one is positive. And you see the life becomes easier. So from 4 equations, we come to 2. Now here we have plus 2. Again, this is positive. Rho 1, 1 minus 2 omega squared average. This one altogether is negative. Rho 2, 2. So rho 2, 2, which is population of excited state. Or consider, to be specifics, rho 2, 2 at 0 is 1, rho 1, 1 of 0 is 0. Rho 2, 2 will damp its value with rate minus 2 omega squared expected. Rho, this is 1/2. Zero. Rho 1, 1 will increase from 0 to 1/2. And then at some point they will achieve 50% population. This is not bad. So we will arrive to the center of the Bloch sphere, right? What makes me not 100% happy that I would love to have relaxation completely going to 0, right? Completely to the ground state, and the population of the ground state to go to 100%. So this is shortcoming of the description in a frame of the classical noisy bath. Classical noisy bath. Noisy bath. So when we consider influence of the noisy bath on the processes of excitation, going from ground to excited, and when we consider rates of the relaxation or emission going from excited to ground, emission or relaxation, they are equal. So we have emission, rate of emission is equal to rate of relaxation what? Not emission, excitation. I need to deprive myself from your markers, otherwise I will dry them really quick. So this is a consequence of classical noisy bath. And this fact that these constants here and there are equal brings us to the equilibrium solution of 50% occupation for both ground and excited. This would be correct in a true quantum consideration if we consider a limit of temperature goes to infinity, right? In the real life, if you want an approach to absolute 0 Kelvin or room temperature, which is not infinity, if you want a solution to come into detailed balance, into equilibrium, which is between 0 and 50%, right? So a necessity to describe arrival to closer to equilibrium, closer to the ground state, brings us an idea to take into account quantum bath, which we didn't consider today. So the actual bath must be quantum. So today we got a terrific breakthrough by considering classical noisy bath, and it gives us T1 constant. So those 2 omega squared is basically the goal is achieved is 1 over T1, right? So we got, so to say, microscopic. 405. We need to done. Stand for all. And I think we are done, right?